Hello, everyone. My name is Jen Morgan, and I'm the Virginia Program Lead for Riot. Welcome to the Riot Lunch and Learn series, the place where we spotlight Riot sponsors. Today, we have with us Tom from Nemko to discuss the prerequisite regulatory requirements for 5G. Just a couple of quick reminders before we get started. This event is being recorded and will be posted to Riot's YouTube channel and uploaded to the meetup page where you registered for this event. If you have any questions throughout the presentation, I will be monitoring the chat. Please place your questions in the chat. I will read the questions out loud as we go through if it makes sense. Other questions will be answered at the end. Please keep yourself muted throughout the presentation so that we can ensure the best audio for the speaker. Tom, I'll turn it over to you.
Okay, thank you so much. My name is Tom Tidwell, and I work for Nemko. We're a test, inspection, and certification body. And I've been working in this field for about 35 years and working for Nemko 29 of those years, going on 30. And my area of expertise, if you will, is wireless, and I am responsible for the international approvals services within the Nemko group. So we're a global group with offices, test labs, and so forth in different areas of the world. So that's me, and I'll get right into my presentation. So I'm going to stop my video and share my screen. Okay, so thought we would talk a little bit about in general about 5G. I know most of you on this call are aware, at least somewhat aware of 5G and networking, so I won't go to too many details in that regard, but this presentation was originally for people of varied experience and background in wireless and the 5th generation networking. Just a few statistics to start with. By 2025, it's projected that 5G will cover 1/3 of the population of the world and account for 1.2 billion connections. And so far, 58 countries, and it's actually 60 maybe since I did this presentation, have implemented 5G networks in the process or have implemented. And 70 other countries have announced plans to implement 5G. So pretty much globally, we're seeing a rollout of 5G networks. The key thing to understand about 5G is that although it does add some new frequency bands to the spectrum that we now use for mobile networking, there will be the existing bands we will still be using. As you probably know, frequency spectrum is not cheap, and it's an infinite resource, or it is not an infinite resource. So we have to use some of the bands that we're currently using for 2G, 3G, and 4G. And because of that, we in addition to adding additional spectrum, we have to sunset or close some of the technologies that we've gone beyond, such as 2G and 3G. Because the rollout of 5G is on a different timeline in different countries, the sunsetting of 2G and 3G is also on a different schedule. So I believe in the EU, 3G has just been sunsetted at the end of last year, I think it was. So they're essentially 4G and 5G. Of course, 6G is coming, but we won't talk about that too much today. But in general, by 2025, most of the countries that will implement 5G will have sunsetted 2G and 3G. One of the issues that we will talk about in this presentation is the fact that 5G, of course, uses wider bandwidths in order to increase faster data and things like video streaming and so forth. And because of the wider bandwidths that are necessary for 5G, they don't always fit just perfectly into the 3G, 4G channels. And so we have to do channel stitching and things like that. It can be a bit confusing, at least for some of our customers, if they're purchasing radio modules, LTE modules and things. It can be very confusing because there's so many different terminologies, and some of them mean the same thing as others. And so if you look at just some of the terms that I've got on here, it can be quite confusing sometimes for a manufacturer of a product. Say someone's making a refrigerator and they want to put in an LTE module. For some reason, they don't necessarily know wireless, and so it is a new world for them. So we'll talk a little bit about network types, and we'll go over some of these terminologies and technology references that fall into, and we'll define what network type they fall into. If you hear 3G and sometimes just LTE, that's still a 3G, and in some cases a 4G technology. As I said, 3G has been disabled in Europe and mostly in the US and Canada. The complete sunset in North America, I believe, is the end of this year. 4G introduced what we call LTE-A and E-Ultra, and that was just the next step on the evolution of the network, allowing faster data rates, more traffic on the network, and so forth. And now we're at 5G NR, or new radio. And this is just an example of the difference in data rates between LTE and LTE-A, 3G and 4G, essentially. 10 times increase. But if we talk about LTE-M, which is LTE for machine-to-machine communication, and narrowband IoT, they have a little bit lower data rate. So for narrowband IoT, this is really intended for Internet of Things sensors that don't necessarily need a fast data rate. So of course, they're narrow band, they don't take as much spectrum. The latency can be a concern depending on the type of sensor that we're using. And if we go to LTE-M, we can see that there's an increase in our capability, our data rate, and the latency is still can be a concern. But if we need higher performance, we would want to, meaning higher data rate, lower latency, and higher density on the network, we would consider 4G LTE-A, Cat6 or higher, or a 5G module. So this presentation really is about 5G. So we'll concentrate a little bit more on that in the rest of the presentation. Of course, the 5G network is not built out globally. So most of your LTE modules will have, they have 5G capability, but they will have a fallback to 4G. Some of them even 3G. So let's talk a little bit about the issue of spectrum. Some existing bands have limitations, and as we talked about with bandwidth. So there's been spectrum harmonization activities done globally through the World Radio Conference. And they meet every 3 to 4 years. And it's the ITUR, the ITU radio organization that puts on the WRC. They're scheduled next year, and on their agenda, among other things, is a global harmonization of the 3 gigahertz 3GPP band 78. That's the most interesting band for 5G because as far as propagation is concerned, it has advantages, of course, over millimeter wave, the really high frequency above 6 gigahertz. And so that's probably the most interesting, and it's also interesting because contiguously it has enough spectrum. There's 500 megahertz there available, so it gives us a lot more room than some of the other bands. China and Japan have backed global harmonization of the 4.8, 4.99 gig band. I'm not sure how far that will go globally, but that is their proposal. And then we'll mention Wi-Fi 6E. That's on the agenda, and it does have some impact on 5G networks. So the 3.5 gigahertz band, we'll call it, it's actually 3.3 to 4.2 gigahertz. This 3.5 gigahertz band is one of the better bands for 5G, but there needs to be more harmonization. Only 200 megahertz of this is really harmonized around the world, the 3.4 to 3.6. And given that, some of the 5G carriers go up to 100 megahertz or even greater, there's a need for greater contiguous bandwidth. And so the ideal is at least to do the 3.3 to 3.8 band 78. And eventually, if we could get band 77 harmonized globally, that would give a good base for 5G and 6G to come. As you know, the spectrum allocation is broken up. The ITU has created these 3 different regions. 1 and 3 are generally use the same bands for mobile networks. And region 2, where we are in Americas, uses a different band than the rest of the world. So the challenge is to create more bands that are harmonized across all 3 regions. This obviously would simplify regional roaming, making that less complicated, and from a hardware perspective especially. So if we look at the 5G spectrum, it's really broken up into 2 broader categories: FR1, which is below 6 gigahertz, and I won't go through all of these, but these are the bands. And as you will recognize, some of these bands are used today for 3G, 4G, and were used for 2G. The supplementary downlink, the base station to mobile bands, those are used when it's necessary to supplement the bandwidth of another band that's carrying traffic, because that greater bandwidth is needed for things like video streaming. So it takes care of some of the housekeeping on the network to free up that communication band that you're doing the streaming on. So it's really there to boost the regular bands. And here is the rest of the sub 6 gigahertz bands that are of importance. The supplementary uplink, by the way, is the same thing going the other direction, obviously, to boost the uplink, the mobile to the base station traffic. Then we have FR2, which is millimeter wave, they refer to it, and it's 26.5 gigahertz band, 24 gigahertz band, and 37 gigahertz band. So 37 to 40 gigahertz. So 5G, when I'm talking to someone who's new to 5G, they often think of it as a technology. But 5G, of course, is just the 5th generation network. So it encompasses many different technologies, new modulation techniques, and new antenna design techniques and control techniques, as well as many other things to improve the reception and so forth. So talking about antenna systems, we're using now something called beam steering. It's been around for quite a while. It's something that has been used in the radio broadcast industry, like for AM radios, especially AM radio stations, to sort of shape their coverage to get as much field strength in the areas that they're allowed to have higher field strength in, and attenuate in the areas that they're not allowed. So to protect other radio stations. So it's been used for a while, but it's used more and more in commercial communication products because now we have the ability to put the computing power that's needed to dynamically steer the radio beam by phasing and doing the beam steering with multiple elements. So we have that computing capability in a small area now because of the developments in microprocessing. So it's just a matter of having multiple antenna elements. It could be 2 to 164. I mean, it could be a huge number of elements, and they're fed in different phases to focus and steer that beam, that main lobe anyway, ideally in sort of a pencil beam to the user with whom it's communicating. This, of course, beam steering and these antenna technologies increase efficiency and also link reliability. So, of course, anytime you have a radio link, an over-the-air link, you're concerned about fading and obstacles within the environment that can disturb the radio propagation. So beam steering allows us to do some of the correction for that and improve our propagation. And it also allows us to reach the user using the minimum required power output rather than just blasting a huge amount of power, RF power. We can be more judicious in the way we put out our radio power density. Something called massive MIMO, and MIMO is multiple input, multiple output, just meaning that both on the receive and the transmit side, we have multiple paths. The massive MIMO is a beam steerable system, and as I said, it can have many, 164 different elements, and those elements, you can have an element that is vertically polarized and an element next to it that's horizontally polarized, so your cross polarization. So you just increase the probability of receiving and transmitting that signal in such a way that the user gets full benefit of it. These are used often in environments like sports stadiums, shopping malls, where you'll have a higher concentration of users. In fact, they're also called the multiple user, multiple input, multiple output. So MU, So let's talk next about the radio access network. So this is more it's not just the software in our current network configuration. It's not just the software, but it involves the software and the interoperation of the different hardware components in the network. So the radio access network is the means by which devices interface with the wireless over-the-air network. And ORAN, of course, stands for Open Radio Access Network. And it's this concept that is adding flexibility and efficiency to the network. Just to talk a little bit about the cellular network, of course, the cellular network as we know it today really started in the 70s. And one of the first actual operable cellular networks was in Finland in 1971. But even before that, even as far back as 1910, Lars Ericsson in Sweden installed a telephone in his car. So I guess you could say he had the first mobile phone or car phone. However, he would have to stop on the side of the road, and he had a special pole, and his wife would get out and connect to the actual telephone wires, and he would make a call. So it wasn't a wireless system, but it was a car phone. But it really wasn't until the late 70s that the first network was established here in the US. It wasn't that Americans engineers were less innovative, but they applied for the use of the frequency band back in 1971. It just took a few years to convince the FCC. The first mobile phone, as you probably know, was developed by Motorola. There's some dispute, but that phone was actually about 11 inches high and weighed about 2.5 pounds, and it cost almost $4,000. Dr. Martin Cooper of Motorola tells it that he made the first call to his rival over at AT&T, Dr. Joel Engel, and he made a call from street level in New York City. It was during a conference, and said, "Hey, I'm talking to you on an actual mobile phone." So talking about the traditional network, we've always kind of divided it into the radio access network and the core. The basic task, of course, in a mobile network environment is to interface the wired telephone network or internet data network with the mobile subscriber units. And to do this, we have the two parts. As the name implies, the radio access network is the radio equipment chain in the network, and it includes the baseband processing, modulation, radio frequency amplification. And in a traditional network, the RAN is provided by a single equipment vendor, and often in one equipment rack. The core, on the other hand, controls the connection to services. So it connects you to the actual wired network. It connects the radio to the wired network, takes care of billing, and routes the calls over the network. And it handles handover from one cell to another, and those functions. As I said, the traditional networks could, I guess, theoretically combine the RAN and core infrastructure equipment from different vendors, but I don't know any that do, because you have compatibility issues and it would be a huge job to overcome those interoperability issues. So traditionally, we've used one single vendor for both the core and the RAN, or at least the RAN, because of interoperability. And sometimes we have to compromise between functionality and interoperability in the traditional RAN, since a network service provider sort of had to use the single vendor equipment. So they may have to install a system that really has more power than they actually need for that particular cell, because that's what that single vendor provided. So talking about the front haul and the back haul, so the front haul is everything from the RAN all the way back to the subscriber devices, and the back haul is from the radio base station system all the way back to the wired network, whether that's using fiber or a T1 dedicated phone copper line, or whatever that might be. So here are some of the goals of the ORAN, or Open Radio Access Network. Its goal is to make the network more flexible, virtual, software driven, which ties in obviously with virtual, intelligent, and energy efficient. The traditional system just doesn't really give the maximum flexibility because of the single vendor issue, and also the fact that it's less dynamic. There's software involved, but most of the traditional system is more inflexible hardware. So flexibility is what's pushed us to this open interface, this idea. So that service providers can create and adapt the systems using different vendors, a variety of vendors' equipment. So we need that open interface to be able to make sure that these systems and these pieces of hardware operate with the best interoperability. And this allows us to implement, as I said, implement solutions for a specific situation. So if we have a cell that needs a specific amount of power, we don't have to put more than is required or less. And it also provides, of course, a more competitive environment, since you're not tied to a specific vendor. And we talk about virtualization of the network, and of course that involves more software. It also involves more AI and less human interaction. So for that, we need near real-time computing in order to put this into practice. And we can then use big data to drive this network intelligence and learn where the traffic is shifted within the specific network, and we can dynamically allocate resources. And that, of course, reduces the service provider's operating expenses, the utility, and so forth. So virtualizing the network involves making more of it software driven, of course. If we look back at the traditional system, we'll talk about now disaggregation of the hardware. In the traditional system, as I said, everything was really in one rack at the bottom of the tower, including the power amplifier. And you just had typically an antenna at the top that was not an active antenna. It was just a passive element. And you ran coaxial cable up the tower and just dealt with the amount of power that you lost in that. We weren't as concerned about utility and that type of thing, and how energy efficient the base station system was. We just blasted more power to overcome the loss in the coaxial cable. Now, by disaggregating the system, we can put the remote radio head up very close to the antenna with a shorter bit of coaxial cable, or directly on the remote radio head, and reduce the amount of thermal energy that we lose in that RF cable. And then we take the fiber optic. We use fiber optic to take the BBU signal and take it up to the remote radio head, amplify the RF signal, convert it to RF, amplify the RF signal right at the antenna. So we save on energy in that way as well. Let's talk about adding intelligence. So I'll give you an example. Say during rush hour, a cell is servicing a main route. We can now, with ORAN, we can scale to accommodate the increase in cell traffic, say in the rush hours, and then shift that capacity from a cell that's covering a less used area during rush hour, and use that for that particular stretch of road or highway when the mobile traffic would tend to be higher. And then we can, in real time, shift those resources to the business park, where everyone is now at their desk streaming Netflix on their mobile phone. Talking about energy efficiency, this is one of the largest costs for a service provider, of course, is their utility costs. And being able to use more energy efficient radio hardware systems controlled dynamically by software and AI, we can save as much energy as possible. So a more virtual network is actually more energy efficient as well. So we really went over this before as I had the illustrations up, but the Open Radio Access forum actually has the standard built so that we can ensure interoperability between vendors. So no more proprietary software and that type of thing in our systems. So makes it easier and more efficient. And the CPRI, the Common Public Radio Interface, now this sends the data from the BBU to the remote unit, the remote radio unit. And for 5G, there's an increase in the demand on the bandwidth of that connection. And as I said, if we're using fiber, that's great, but we're even being pushed for more data and lower latency. So even fiber's starting to be stretched as far as the capability. The eCPRI splits the functionality of the BBU, and we can actually move some of the BBU functionality up to the remote radio unit. So more and more we're able to smartly group these systems and the hardware together. This is just, won't really belabor this too much, but the RU, the radio unit. It's also called the remote radio unit or the remote radio head. But just remember, with each of these components of the system with ORAN, they can be from different vendors and still interoperate. And we talk about distributed and centralized units. So this is just an illustration of that for reference. It brings up some regulatory issues because now we have hardware from different vendors, and an organization such as Nemko, if we are going to test or certify that unit, we have the problem that, okay, that unit complies with the technical regulations with vendor A and vendor B's equipment, but what if we put in vendor C's equipment, BBU? Is it still going to comply as a system? So there are some discussions, a lot of discussions now with the regulatory bodies like the Federal Communications Commission to be able to determine what do we do there, what gets labeled and what is actually certified. Is each piece certified? Obviously, you have to make some assumptions about compliance because it's unknown what this piece of hardware is going to be connected to. Of course, interoperability is an issue, but for the regulators, it's usually a secondary issue. The primary issue, of course, is interference and compliance with the technical regulations of power output and bandwidth and so forth. Talking about software and from a regulatory standpoint, more and more, when we test and certify a piece of hardware, we also have to think about the firmware and the software that control it, because those components, the firmware and software, set the functions such as the modulation type, the bandwidth, and all sorts of things. So power output. And so if there's a change, for example, and we've certified a piece of hardware and it has embedded firmware software that controls these functions, if we get a revision of the software, now we have to worry that it could have changed the compliance of the product. So how do we ensure that this mix of components from various vendors and these essentially software-defined radios are compliant when they hit the market? I'm going to briefly talk about Wi-Fi because it does have some connection to 5G, mainly because more and more traffic is being offloaded to Wi-Fi, which is great in that it frees up the network, the mobile network, but Wi-Fi now is having to keep up. From an evolutionary standpoint, has to keep up with the demand for more data, faster data rate, and more users. By the end of this year, they have estimated that 60% of mobile traffic will have been offloaded to Wi-Fi, which is kind of an incredible thing when you think about it. And 51% of all IP traffic will be over Wi-Fi. 79% of the global data traffic, now that's including wireless and wired, will be video content, which of course demands higher data rate and bandwidth. So these are the drivers for Wi-Fi evolving in its capability. Now we have the Internet of Things, the IoT, where in some cases we need lower latency. And of course, now we have antenna design that can give us better signal propagation. This is really just for reference to give you kind of the accepted Wi-Fi 1 through Wi-Fi 7 designations. Because spectrum, as we said before, is a finite natural resource, it's shared among users. Governments and regulators around the world are I don't want to say fanatical, but they're very concerned about protecting spectrum that has been licensed to a specific user. I mean, obviously you have spectrum auctions where service providers pay a lot of money for spectrum, and of course they don't want to be interfered with by someone's Wi-Fi or someone's garage door opener, for that matter. So let's look at some of the Wi-Fi frequency bands that are used, and we can see that in some cases they're close to some of the LTE and the 5G bands that we're talking about for our networks. Each of these bands has different issues and challenges. Obviously, the 2.4 and 5 gigahertz band, they're not great for propagation. You'd be better off at 400 megahertz, but or even lower. But the 2.4 and 5 gigahertz bands have been harmonized globally for the most part, so, and designated as unlicensed use. So, you know, the user doesn't have to get an individual license, but it's always based on non-interference. So there has to be testing, and there have to be things done to make sure that unlicensed devices operating these bands do not walk on the licensed services, such as the mobile network. So now we have Wi-Fi 6 and Wi-Fi 6E. The main difference is in the frequency band that's used. So Wi-Fi 6 is the EU designations and many of the other countries in the world. There are some restrictions in these bands, some of the sub bands here that are restricted for indoor use only. Now, Wi-Fi 6E requires automatic frequency control, and that's just the device has to be able to change frequency to a different channel when it senses. Some countries are planning to require that Wi-Fi access points, or gateways, are sometimes called, support Wi-Fi 6E. So as early as well, this year, Saudi Arabia actually, and some countries next year that it's planned. They also require such devices operate in LTE bands that are used in their countries. So they don't want users purchasing a device that, you know, suddenly they find out can't be used on the networks in their area. This just gives you some information for reference about the rollout of Wi-Fi 6 and 6E. And speaking about Wi-Fi, it's often the first link in the Internet of Things. And in some cases, IoT requires low latency. So if we take a factory, you know, where you have a machine and you have a sensor on it, that it could be important if the machine, or if the sensor senses that the machine is overheating, then we need to send a signal and shut that down, you know, have the computer shut that down. So if we, you know, went through the whole through the whole process, going from the IoT sensor, going to the cloud network, and then back down to a computer, there's more latency. And, that machine in that factory might have overheated to the point where suddenly, it's destroying raw materials and causing a big problem in production, where we want to be able to sense it and shut it down. So we would use edge computing in that case. And so that's, mostly going to just be the Wi-Fi part of the network. Just wanted to briefly talk as I conclude here about what this means from a regulatory standpoint and a test standpoint. Because of the developments in antenna technology, whereas we used to do a lot of the testing, right at the RF pipe on the device that we're testing, now we have to include the antenna, because now that's a dynamic part of the whole system. So we have to do over-the-air testing. And we look at things like total radiated power, which is the power, at a point in space. We have to do antenna pattern testing now. We have to test up into the millimeter wave band. So, in our labs, we're having to test even up to 300 gigahertz in some cases. So that's quite a challenge. We have issues with RF exposure. We have to test RF exposure, and traditionally that's been done with a mathematical prediction, but now we have so many systems that are operating above 6 gigahertz, and the best way to do that is to measure the power density, and that can be quite involved if you have a system that is multiple antenna elements and you have different beam configurations. So you have to do a lot of different testing to test the power density on those systems. And as I mentioned before, the automatic frequency control. These are just some of the things that we have to now test that we didn't before. So really, just to summarize, the 5G evolution has been a development for better modulation. We've had to do things like coordinate spectrum usage in real time dynamically, increase the data bandwidth capability, and also increase that data latency in many systems. Not everybody is on board with 5G. Actually, in some of the first systems that were installed, 5G systems that were installed in China were in Wuhan, which led people to believe that the Omicron, or the virus, was started because of 5G. We know that's not really true, but circumstantially it looked to be the case to some people. So there have been protests and so forth. I guess now I can just open it up to some questions. If anybody has any questions, I'd be glad to take them.
Thank you, Tom. That was a great presentation. I really appreciate it. We're going to now open the floor to questions from the chat window. If anybody has any, please put it in there and I will go through the list. Tom, I have to say that I have a 5G phone and it gets terrible reception in certain buildings and certain places. So this gives me hope that Maybe I don't have to yell at Verizon. If anybody
Yeah.
works for Verizon, no judgment, just personal.
Yeah, I think Verizon uses, well, they use a millimeter wave system at the moment. In fact, most of the carriers in the US that are doing 5G, I think are started with millimeter wave, the higher frequency. So
Yeah. It's funny, I was at the dentist, which is right next to the Verizon store, and I didn't get signal in the dentist office. So I don't know.
yeah, you're going to find it, mostly, as I say, in shopping malls and things. We're going to have a higher density of users, but the actual, the propagation is pretty short. So you're not going to be able to get it, for a mile or two away.
One of the questions in the chat is, can you share the country list of 6/6E requirements by date again?
Yeah.
Awesome.
Did I don't know if I put the dates on there.
There's a year and under implementation.
Okay, let's see. Find that slide. This the one, maybe?
If that was your question in the chat, can you confirm that?
I'm sorry?
I was just saying if the person who put the question in the chat confirmed that they're getting what they need.
Yeah, we have the year, the implementation by year. Actually, Taiwan here, I notice it says under consideration, but they've since decided that they would implement it. So they actually started in April or May of this year. So they're implementing this entire band.
Awesome. Are there any other questions at the moment? I'll leave the floor open for another 60 seconds. One of the questions that just popped in is regarding the additional testing for 5G, what percentage of costs increase in testing should we expect?
It's maybe 8-10%. It's not necessarily the it's more the fact that there's more testing on systems that have complex antenna systems, especially where we have to do a lot of over-the-air testing, and that just adds to both the setup time and the number of configurations that we have to check. So it ends up adding more time. So depending on how complex the system is, particularly the antenna, we could get, you could get a 30 or 40% increase in the amount of cost because of the time. But in general, we don't see a lot of massive MIMO systems, in fact. So I would say across the board, it's maybe 8 to 10% just to reflect additional time and additional equipment that we have to purchase.
Awesome. Any other questions, folks? Okay. Well, thank you so much, Tom. What's the best way that people can get in contact with you if they want to?
Yeah, best way is my email, and it's Tom, TOM, .tidwell, TIDWELL, at Nemko, NEMKO.com.
Okay, I just popped your email in the chat for everyone.
Cool.
And thank you so much. I really appreciate it.
You're very welcome. I enjoyed it. Thanks,
Great.
everybody, for your time.
Thank you. Everyone have a great day. We'll talk to you later.
Okay.
Bye.
Bye.